In this video, we'll be looking at set theory. So what is a set? A set is an unordered collection of elements. So if my set contained numbers, it could contain 1, 7, 3, 6, 5, 2, etc. It's an unordered collection of elements. A couple of the common sets you're going to see in discrete mathematics. One of them is the empty set. It can be written like this or like this. And an empty set is a set with no elements. It's empty. And another set you're going to see is the set of all natural numbers, which is written as n. So that would be 0, 1, 2, 3, 4, 5, etc. And you also have z, which is the set of all integers. So negative, positive, and 0. You have something very similar, but only with the set of all positive integers. 1, 2, 3, 4, 5, etc. Not 0, because 0 is not positive or negative. Then we have r, the set of all real numbers. Very similar again, but with the set of all positive real numbers, kind of like how we did for z. And then we have c, the set of all complex numbers. Equal sets. If you look closely, we have the universal quantifier again, which if you don't remember what that is, go back to video number 1. I explain it towards the end. Over here we have the mathematical definition of an equal set. An equal set is basically two sets that contain the same elements. Exact same. Neither set has any more or any less elements. They have the exact same ones. So our mathematical definition reads, for all elements x, x belongs to A if and only if x belongs to B, which means that x would be the element within the set. And so if the element within set A, if an element is in set A, then it has to be in set B. Subsets. Again, we have the universal quantifier, and what this reads is, for all elements x, if x belongs to A, then x belongs to B. Which means, if we put this into an example, let's say A is, this is our set A. That's horrible. Let's try that again. We have our set A is 1, 2, and 3. And our set B is going to be 1, 2, 3, 4. So A contains elements that are in B. B contains all elements that are in A, but A does not contain all elements that are in B. That means that A is a subset of B. Think of it like a Venn diagram, right? Like, this contains all common elements that B has, but B does not contain all elements that A has. Meaning that A can go into B, but B can't go into A. So this can also be written as A is a subset of B, like this, and you're going to see there's a line at the bottom, because A can still have the 4, and these can be equal sets. So a subset doesn't prevent two sets from being equal. Now we have a theorem to look at, which we're going to come back to. I'm just going to explain it now. Let's say we have a set S, for example. Any set, this is just a set S. For that set, we have an empty set as a subset of S, and S as a subset of S. So an empty set and the entire set as a subset of S. Now, the Venn diagram, which we're going to look at in a second. A proper subset is mathematically written like this, which means for all elements x, if x belongs to A, then x belongs to B. And there exists at least one element x in which x belongs to B and x does not belong to A. which means how in the last slide we saw that A contained 1, 2, and 3, but B contained 4. So that makes A proper subset of B, meaning they cannot be allowed to be made equal sets. And that's what separates a subset from a proper set, in proper subset, in that a subset can be an equal set, but a proper subset cannot. And that's basically what the Venn diagram shows. And this is how it's written. A proper subset is written without the line under it. A power set. A power set is the set of all subsets. So let's say, for example, we have the set 0, 1, 2. Let's call that set A for this example. Oh, I need a pen. Let's call this set A. Okay. And that's 0, 1, 2. Our set A, first it contains an empty set, right? Every set needs to contain an empty set. Then we have a set for each element. So 0, we have 1 for 1, and we have 1 for 2. And then now we need to do combinations, 0, 1, 0, 2, and then 1, 2. Now the question has to be asked, why not 1, 0? Why not like 2, 0? That's because this is a set, not an ordered pair. 1, 0 and 0, 1 are the same sets, so you don't have to repeat them. Therefore, 0, 1 covers it. So we have a set for 0, we have a set for 1, 2, 0, 1, 0, 2, 1, 2, and then finally the entire set. Now, this should look familiar to you. Let me tell you which parts should look familiar. This part and this part. We have an empty set as a subset, and we have the entire set as a subset. And if we look back 2 slides, we said that for any set, we're going to have an empty set as a subset and the entire set as a subset of that set. Which means that this proves our theorem right here. This power set right here. It shows that the empty set is a subset of what we called set A, and the entire set A is a subset of set A. Now let's look at an example. What is the power set of an empty set? I remember this question kind of stumped the entire class when the professor presented it. It's not actually that hard. The power set of an empty set, let's remember our theorem, because that's what's going to give us the answer. That's so bad. Okay, that's better. Our set has to contain an empty set, and it has to contain the entire set itself. Now, this set itself is an empty set. We're repeating elements here, and we don't need to do that. So that means that the power set to an empty set is an empty set. We only have to write any repeating thing once. So that means the power set of an empty set is the set containing an empty set. So then what's the power set of a set containing an empty set? The power set, let's look at our theorem again. We need an empty set for any subset of a full set. So we have an empty set, and then we have the entire set itself, which is this. So the power set of a set containing an empty set is an empty set and the set containing the empty set itself. And those are your answers to these 2 questions. Now, the Cartesian product. This one is different from sets in the fact that over here you can see that AB and BA are not the same. But let's first tell you what a Cartesian product is. A Cartesian product of A and B is the set of all ordered pairs AB where A belongs to set A and B belongs to set B. It's written as this, the Cartesian product of A and B, and the Cartesian product of A and B is not the same as B and A. I know we're saying product, but swapping these gives you very different results. So it's not exactly a product per se. It's not like multiplication. So the Cartesian product of set A to B is not the same as B to A. Unless A and B are the same, which means if they're the same, or if they are both empty sets, which also kind of means that they're the same because they're both empty. But let's not get into that. They could either both be empty or both have the same elements. The Cartesian product of A to B would give you a kind of like an ordered pair of AB, and that is not the same as what the Cartesian product of B to A would give us, which would be BA. I'll explain that more in the next slide. The subset R is called the relation from set A to set B in the Cartesian product from set A to set B. The elements of R are ordered pairs in which the first element belongs to A and the other to set B. Before we move on to the next slide, I'm just going to explain this part using a graph. Let's say we have a graph right here, a really bad graph, but all right, so we have a graph. Let's say A contains the numbers from the x-axis and B contains the numbers from the y-axis. If we keep the set entirely empty, then it doesn't matter if we're looking at the Cartesian product from A to B or B to A, the graph is going to look the same. But let's also consider, let's say that we have the function y equals x. So that would kind of look like this. If our b is 1, then our a has to be 1. If our b is 2, our a has to be 2. If our b is 3, our a has to be 3. They are the same, which means that no matter how you swap them, if a is 1, b is 1, if a is 1, b is 1, they're gonna look the same. Therefore, if they are the same sets, or if they're empty sets, they're gonna look the same, but not otherwise. One more thing. Another way to explain it is, let's say you have the graph y equals 2x. Y equals 2x, right? X. All right. Now that would kind of look like, let's say this is A first, and this is B. That would kind of look like this. Y equals 2x. It's a steeper slope. But if you swap A and B, then it would look like this. These are very different graphs. So that's why you can't use them, you can't exchange them. And over here, you can see that. So the Cartesian product from A to B. Let's do a little exercise here. Cartesian product from A to B. Our A is 0 right now. And our B is also 0. Therefore, the first pair we have is 0, 0. And now, our B changes to 1. So we went from 0, 0 to 0, 1. So that's our next pair. And now they both change because we've reached the end of set B. That means our A, we can now move on to 2. And we have to pair that with the 0. So 2, 0. And then our next number in set B would be 1. So we can go from 2 to 1. That's right here. And then we've reached the end of set B. So now we can look at A's last element, which is 4, and B's first element, 0. We went from A to B. We're going from A to B, not B to A ever. We're going from A to B for the Cartesian product of A to B. And then our last number for B is 1, which means we have to look at 4 to 1, and that gives us 4, 1. Now, our Cartesian product for B to A. Let's look at what that would look like. Let's remove these red lines. And now, in blue, we're going to do B to A. Okay, so we're going to have 0, 0 first. Right? So that's over here. And now we're already going to see that this is going to look a little different. We're going from B to A. So now our A is 2. So we're going from 0 to 2. And so 0, 2. And now our A is changing to 4. So we're going from 0 to 4. Over here we have 0, 4. This is very different from what we have from the Cartesian product of A to B. Over there we have 4, 0. We have 2, 0. And, well, both of them are 0, so we have 0, 0. I guess we have one common one. All right. And now we've reached the end of set A. So now our B can change to 1. So this is 1. And our A is 0 again. We start from the beginning. So now we have 1, 0. And now we can move on in set A and go to the number 2. And we have 0. No, we have 1, 2. And lastly, we've reached the last element in set A, which would be 4. We go from 1 to 4, and that gives us the pair 1, 4. So you can see how these are very different. Over here we have A is 4 and B is 1. Over here we have the same thing, but in the different order. We have to go from B to A, and over here we have to go from A to B. We have 4 and then 1. Over here we have 1 and then 4. All right, set operations. In this slide, we're going to talk about unions. The unions of set A and B are denoted as, well, A union B. It's written like this. The union of sets A and B contain the elements in A and B put together, not or, and. Because you're merging them. They're a union. It's kind of like basically a Venn diagram where you consider every element. You're merging them all. Now, A and B contain 0, so you only have to write 1. Again, you don't have to repeat elements in a set. So we're going from 0, and then we have 1, and then 2, and then 3, 4, 5, 6, 7, 8, 16, 32, 64. And that's everything we're seeing here. So we merged both sets. It's a union. And that's pretty much straightforward. All right, now an intersection. I want you to picture, or not picture, I'll draw one for you, a Venn diagram like this. An intersection is where both of these circles, let's say this is for A and this is for B, the intersection is where these circles intersect. So whatever common elements that set A and set B have is the intersection. And it's denoted like this. It's written like this. All right. So over down here in the example, they both have in common 0, 0, and they both have zeros. They both have 2s, they both have 4s, they both have 8, and that's about it. So the intersection of A intersection B would be 0, 2, and 4, because those are the only 4 elements they have in common. Set operations, we're going to look at the difference now. The elements of set A minus the elements of set B. Okay, so in the example, that's the best way to explain it. Let's say you have in set A all of these elements, and in set B you have these. Your subtracting every common element between these two sets and only keeping the ones that are unique to set A. So A minus B. You don't care about the ones that are unique to B because you don't need B anyways. All you need is to remove the common ones. So that would be 0. Let me choose a different color. Okay, that would be 0, 2, 4, and 8. You don't care about the other elements in set B. These are irrelevant to you because you're doing A minus B. So then these are the only numbers that you have left. Therefore, 16, 32, 64 is your set for A minus B. If this was B minus A, your set would be whatever I scribbled out in purple for set B. So that would be 1, 3, 5, 6, and 7. That would be B minus A. Set operations, we're going to look at a complement. The complement is known as the universal set minus whatever set you have. Let's say, for example, it's set A. So the universal set contains all elements. Any element you can think of, 1, 2, 3, 4, 5, infinity, whatever. It contains all elements. So, whatever set A contains, the complement of that would be everything else. Like whatever is not in set A is the complement of set A. So let's say set A contains 3 and 4. The complement of set A would be any negative number and any positive number that isn't 3 and 4, 0, whatever. Uh, like infinite numbers in universal set. But the complement of set A cannot include 3 and 4, which means obviously the complement of the complement is set A itself, which would be 3 and 4. I hope that made sense. Basically, basically a complement is whatever is not in your set A. The complement of set A means you disregard what's in set A and look at everything else. That's the best way I can put it. Okay, so here are a couple Venn diagrams. Whatever is shaded in blue is what you're supposed to look at, which means that the Venn diagram for A union B, you can see that everything is in blue. So you're supposed to consider that your A union B set. So A union B, the sets would look basically whatever shade in blue. So everything that's in set A and set B, that's what A union B would be. And for the intersection of A and B, you only look at the intersection, whatever sets A and B have in common. So whatever is in blue over here is what you're looking at for the intersection of A and B. And for A minus B, you only look at what's unique for A. Not what's intersecting, not whatever's in B, only what is unique to A. So I hope these Venn diagrams help make it clear if it wasn't clear in the slides before. And set identities. These are very important for when you do proofs with sets. The first identity would be the identity law, which is A intersection the universal set is A itself, which means that universal set contains everything, and A only contains whatever it contains. Therefore, the only thing they have in common is whatever is in A. Everything that's in A is what A and the universal set have in common. So A intersection the universal set is A. A union an empty set is A, because you're merging A with no other elements. We have the domination laws, which is A union the universal set is the universal set. Obviously, because you're merging A with everything, basically. So you're obviously going to get everything when you merge it. And A intersection empty set is an empty set because you're merging a set with elements with a set that doesn't have elements. So you're going to get nothing. So this is an empty set when you find the intersection of A and an empty set. Idempotent laws. A intersection A is A. Oh, hold on. This is over here. It's supposed to be union. Right. Pretend that's union. And A union A is also A, obviously. Now, I think last slide I mentioned no, 2 slides ago, I think, complementation laws. So the complement of a complement is A. It's kind of like a double negative. So that means that since the complement of A means whatever is not in set A, that means the complement of the complement means whatever is in set A. And the commutative laws, A union B is the same as B union A, and A intersection B is the same as B intersection A. And that's pretty much common sense. The associative laws. A union B union C is the same as A union B union C, because you're merging everything together. A intersection B intersection C is the same as A intersection B intersection C. Distributive laws. A union B intersection C is the same as A union B intersection A union C. I guess you're distributing the unions and you're intersecting them. All right, so the same goes for intersections, kind of. So A intersection B union C, A intersection B union C is the same as A intersection B union A intersection C. These make more sense when you kind of apply them. All right, more set identities. I didn't say we're done. Complement laws. A union, the complement of A, is the universal set, because the complement of A is whatever is not in set A, and if you combine whatever is not in set A with whatever is in set A, you have everything. So that would be the universal set. A intersection, the complement of A, would be an empty set because they have nothing in common. The complement of A quite literally means that whatever counts as the complement of A is not in set A. The absorption laws. So we can read this as A union A intersection B equals A. Because what you're doing is, here's a Venn diagram. A, we have B. Here's your intersection, and you're doing a union with A. So basically, you're just getting A. So therefore, A union A intersection B is A. And A intersection A union B is also A, because you're only finding the common elements with set A with the merger of A and B, which is just A. And finally, we have De Morgan's laws. The complement of A intersection B is the complement of A union the complement of B. And the complement of A union B is equal to the complement of A intersection the complement of B. So here we have a proof using the set identities. So we have to prove that A intersection B, the complement of A intersection B is equal to the complement of A union the complement of B. So first we have to write what we start off with right here. And that equals what we have right here. X does not belong to A intersection B. So for any element X, the X does not belong to A intersection B, because we're finding the complement. So then we have the negation of that. So the negation of x belongs to A intersection B, which is the same as the complement of A intersection B. X belongs to A intersection B, and we're negating that. And then we kind of expand the negation using the definition of an intersection, which is the negation of x belongs to A and x belongs to B. If we look back at the definition of an intersection a couple slides back, then it will make more sense why I wrote this. But basically, that was on the slide. The mathematical definition, when I said that was important, you really need to look back at those to understand these proofs. And then the next step would be to use De Morgan's laws, which I explained this part in video number 1, if you go back to it, in which the negation of this entire thing means you have to swap these signs. So this is and, you have to make it into or. So the negation of the negation of x belongs to A, or the negation of x belongs to B. And then throw in the negation signs again. So x does not belong to A, or x does not belong to B. And using the definition of a complement, you can say that x belongs to the complement of A, or x belongs to the complement of B. And by the definition of a union, you can say that x belongs to the complement of A union B, which means complement of A union B is your answer right here. Now let's kind of look back at these definitions so you know how to use them. The first thing we look at is the definition of a complement. So let's look at that first. Let's go back a couple slides. Right here. We are saying for a complement that x does not belong to A. Is basically what we're saying. X belongs to the universal set, x does not belong to A. But we don't need the universal set for that problem, so don't let that confuse you. X does not belong to A. And it's kind of similar to what we said. X does not belong to A intersection B, which is what we're trying to prove. So x does not belong to that, which is the first step we did. The definition of a does not belong sign basically means that you negate the belong sign. It's pretty much common sense, that one. And then the definition of an intersection. Let's look back at that. The definition of an intersection, right here. Intersecting set A and B would mean x belongs to A and x belongs to B. Let's see if that's what we said. By the definition of an intersection, x belongs to A and x belongs to B. Oh, well, you got a little sneak peek there. Okay, x belongs to A and x belongs to B. Man, De Morgan's law, that was in my first video, so I can't go back to that. But if you remember it, then basically you can't just distribute a negative sign. You have to swap the one in the middle too. All right, now we do, again, the definition of a does not belong sign. We throw in the negation sign again, so we put a does not belong sign in there. And now we have to look at the definition of a complement, which we already saw, but we're kind of reversing it from what we had before. So we went from for the definition of complement, we went from x does not belong to A intersection B, and then we went into kind of a technical the terms there, and now we're throwing the complement sign in instead of the does not belong sign. We need to make them complements, which is what we're trying to prove individually. And then by the definition of a union, we need to look at the definition of a union. That's a horrible line. The definition of a union. All right. X belongs to A or X belongs to B. Let's see if that's what is written. Right here it says X belongs to A or X belongs to B, which means it's a union. So we can write it like this. Therefore, we get this answer. You really need to memorize the mathematical ways that they're written and not just the concepts. So those definitions that I showed you are really important to remember for the set theory proofs. Now, you got a sneak peek, but we'll go ahead and look at proof number 2. Let's prove that the complement of A union B intersection C is the same as the complement of C union the complement of B intersection the complement of A. Okay, so first we look right here. We're basically just throwing this in, and that equals to the complement of this intersection the complement of B intersection complement of C. And that's by the first De Morgan's law. And we can, using the second De Morgan's law, we can say that equals the complement of A intersection complement of B and union the complement of C by the commutative laws of intersections. We can say that we're basically just swapping places. The A intersection signs were here, and now they're over here. And now we're just swapping the B union C, the complement of B union complement of C. We're just swapping places because the unions of both of them basically equal the same thing. So you can swap the sets with the union sign or an intersection sign, just not for the Cartesian product. And this one was pretty much common sense. All right, now the principle of inclusion and exclusion. So let's say we have a set S. There are exactly n number of elements in the set S, where n is a non-negative integer. We call S a finite set, and n is a cardinality of S. The cardinality is notated as this right here. You could write it like this. All right, so an example. So basically what they want you to do here is think of this as a Venn diagram. Think of that as a Venn diagram in your head. So, well, for now, we're going to do it on the screen. But you should be able to picture a Venn diagram of A and B. Now let's say, that's actually a horrible Venn diagram. Hold on. A, B. Okay. Well, now we need A union B, right? So we need whatever is in A, whatever is in B. So we have whatever is in A, whatever is in B. And that would mean include these common elements, right? So whatever's in A, whatever's in B, and you have to subtract what's intersecting. Otherwise, they'll repeat. The cardinality what they want you to do here is think of it practically a little more. Let's say A has the numbers 1, 2, 3. B has the numbers 4, 5, 6. And what they have in common is 7 and 8. So basically, imagine if I said, give me A union B. What you would do is first say A contains 1, 2, 3, 7, and 8, plus 4, 5, 6, 7, and 8. Now you have two 7s and 8s, so you have to subtract what is intersecting so that you only have it once. Therefore, this is A union B. 1, 2, 3, 7, 8, 4, 5, 6. Right? You don't want anything to repeat. And that's basically what this is saying. So it's kind of more of a practical thinking. Okay, and that's the end of the video. Please be sure to like and subscribe. And our next video is going to be about number theory.